right, lesson 2.12, logarithmic function manipulation. So our skills and learning objectives for this lesson are to apply the properties of logarithms to evaluate expressions and graph functions, use properties of exponents and logarithms to simplify and evaluate expressions, and to recognize the graphic translations of logarithms related to the product, power, and change of base property. Okay, so we start out talking about the properties of logarithms. And it says for any positive numbers m, n, and b, where b is not equal to 1, and p, any real number, the following properties apply. And so if you remember your your exponential rules, like when you multiply, you add the exponents, when you divide, you subtract the exponents. Of course, they're both with like bases. The same rules apply with logarithms as well. So you have the product property that says if you have log base b of m times n, you can rewrite that as log base b of m plus log base b of n. So if you have two things being multiplied, if they're being multiplied, you can separate them by addition, and they both get the log base b. Same thing if it's a natural log. Remember, its base is just e. So if you have natural log of m times n, that's equal to the natural log of m plus the natural log of n. Then you have your quotient property, which is the division. So if you have log base b of m divided by n, so two things being divided, then with the same base there, then you can separate them as log base b of m minus log base b of n. Just remember, what goes on top will go first, okay? So if they're being divided, you can separate them by subtraction. And then you have the power property. The power property just says if you have log base b of n raised to the p, that is equivalent to p times log base b of n. So this power here just kind of bungees over in front of it, or if it's in front, it can bungee back to the exponent. So it can go between being the coefficient and the exponent. Same thing if we have the natural logs. All right, so look at example 1. It says expand the following logarithms using properties. All right, so the first thing I notice on A is we got log of 8 times x times y to the 4th. Now don't forget, a number and a variable side by side means they're being multiplied, okay? So we got three different things here that are being multiplied. So we can separate them. Remember, when you multiply, you can separate with addition. So you're going to have log. It doesn't have a base written, so we know that that is base 10, or we don't have to write it, of our first, plus log of the second thing being multiplied, plus log of the third thing being multiplied. Anytime you have log of a number, you need to check and see, can you simplify that? So using that, remember we had, let me change colors here. So remember we knew that if we had log base b of x equals y, then we could rewrite it as b to the y equals x. So when I have log of 8, that's equal to y, I know my base is 10, my x is 8, and my y is y. So when I do b to the y equals x, is there any way I can solve for y? 10 and 8, I can't get like bases, so I cannot. Since I cannot simplify that to be a whole number, we leave it as log of 8. And then I just have log of x plus, but here I do have that exponent. And so because we have the exponent, remember if we want to expand it, we're going to take it and put it as the coefficient, because to write it out, 4 log of y is longer than log of y to the 4th. I don't have any more exponents. There's no log of numbers that I can work out. So that right there is our answer in expanded form. All right, look at B. B says we have the natural log of the square root of x squared plus 5 all over x. First thing I notice is we have a division. So we know that when we divide, we can subtract them. So that means we're going to rewrite it as the natural log of the top minus the natural log of the bottom. Now remember the square root, we had that thing we talked about that if you have a root of a base and an exponent, that's the same thing as that base raised to the exponent over the root. And so remember that if we have the square root, that's the same thing as saying our base raised to the exponent. It doesn't have an exponent written on it, so it's a 1 over the root. It's a square root, so it's 2. And I can't do anything to the natural log of x. But now that I've rewritten it like this, we do have this exponent, so I can move it, bungee it, as the coefficient in front of its logarithm. Now this x squared plus 5, notice we put it in parentheses because it's together underneath that square root, so we're going to keep it together. We're still going to take the natural log of the whole thing. If you wrote it as the natural log of x squared plus 5, then people or computers, calculators, everything reads it as the natural log of x squared, gets an answer, and then adds 5 to that answer, okay? That is not what we want. That's not the same thing. So therefore, you have to put it in the parentheses to show it's together. And it was together underneath that square root. All right, so let's see. We don't have anything being multiplied. We don't have anything being divided. We don't have any exponents. No radicals. We are in expanded form. All right, example 2 wants us to do the opposite. Now it wants us to condense the following. So, look at A. We have the natural log of x to the 5th minus 2 natural log of xy. Now, we do have things being subtracted, but it's not a natural log minus a natural log. It's a natural log minus 2 times a natural log. So we've got to get rid of this 2. So we're going to move it as its exponent. So this becomes a natural log of x to the 5th minus the natural log of xy, both squared. Now we have a natural log minus a natural log, so we can use our quotient property. So we're going to write down natural log one time, and then it's going to be a fraction. What's first goes on top, and what's second goes on bottom. Now I recognize I have x's on top and bottom, so I know I'll be able to simplify that. But first I need to distribute that square to the x and the y. So this is the natural log of x to the 5th over x squared y squared. And then we can simplify this. So this is going to give me the natural log, x to the 5th divided by x squared. Remember, when you divide, you subtract the exponent. So 5 minus 2 is 3. So it's going to give me an x cubed on top, because that's where the 5 was. And then I still have my y squared on bottom. And so, let's see, we don't have anything being added. We don't have anything being subtracted. And we don't have any coefficients. So we are in condensed form. All right, on B. So B, we have 3 natural log of x cubed y plus 2 natural log of yz squared. Well, I notice they're being added, but again, I've got 3 times the natural log of something plus 2 times the natural log of something. So we have to get these coefficients to move as the exponents. So this becomes a natural log, and even though this wasn't in parentheses because it's being multiplied, it's all together. So now I'm going to put it in parentheses. Not sure why they really didn't do it to begin with, since they did it on the second one there, but whatever. So then we got the natural log of our yz squared raised to the 2nd. I'm going to go ahead and simplify both of these parentheses pieces. I'm going to go ahead and distribute this exponent, and I can do that because there's no plus or minus signs inside the parenthesis. So remember, that becomes power to a power, and we multiply the powers. So this first one becomes the natural log of x to the 9th, y to the 3rd, plus the natural log of y squared, z to the 4th. Now that we've got a natural log plus a natural log, we can combine these, and because they're being added, we can combine them with multiplication. So it's going to give us a natural log of x to the 9th, y to the 3rd, times y squared, z to the 4th. And then, let's see, we do have some like things here. We can go ahead and multiply. So remember, when you multiply with like bases, you keep the base and add the exponents. So we have the natural log of our x to the 9th, y to the 3 plus 2, which is 5, z to the 4th. Got a single logarithm. I have no coefficient. There's nothing being added. There's nothing being subtracted. No logs being added. No logs being subtracted. So that is our condensed form. All right, then it moves on to evaluating logarithms by changing the base. So we have a change of base formula. which if we start out, it says for positive real numbers a, b, and x with a not equal to 0 and b not equal to 1, if we are given log base b of x, we can change it to different bases. So the first one here just says, let's use base a. So if we're going to go to base a, which you're going to take your log base b of x, to change it to base a, you're going to put log base a on top and bottom of a fraction. And it's going to be log base a of x over log base a of b. If we wanted to go to base 10, then our log base b of x would become log base 10 of x over log base 10 of b. Or if we wanted to go to base e, it would be log base b of x equals natural log of x over natural log of b. Because remember, natural log is log base e. And so the hardest part to this is to remember which number goes where when we go to use it. Well, I can remember that the little b is subscript. It's already written down below, so it's always the old base is what's going to go on bottom, which leaves the x to be what goes with the top, okay? So it's just log of your new base of the x over log of the new base of the old base every time. All right, so why might we use this? Well, we used to not have calculators that would actually do a change of base, or it was really hard to get them to do it. So therefore, we would just be able to type it in our calculator that way. It's kind of silly. They already taught you in a previous lesson how to type it in the calculator using that alpha window. And now they're going back and saying, oh, let's do the change of base formula. But it is useful at times, and it does say that we need to learn it. So here we go. All right, so let's evaluate the logarithms by changing the base. And so on A, let's go to base 10. So I've got log base 3 of 13. And so I know that's going to be log base 10 of 13 over log base 10 of 3. And remember, if it's base 10, we don't have to write it. So in your calculator, type in log 13 divided by log of 3. Now don't forget, when you hit the log button, it opens a parenthesis. So after the 13, you have to make sure to close it. Otherwise, you're taking log of a log. Okay, and then log of 3, and you really ought to close it after that last one. All right, so type it in your calculator, hit enter, and let's go to 3 decimal places. So I got 2.335. Let's see, on B, let's go to base E. So we're going to have log base E, which is my natural log of 10 over log base E, which is my natural log of the old base 6. So again, I'm just going to type in natural log. It's going to open a parenthesis. I'm going to type in 10, close a parenthesis, divided by natural log. It opens a parenthesis 6. I should close my 6 and hit enter. And we should get 1.285. And then C, it doesn't matter on any of these which way you go. We could go to base 2, which I think is what it's really kind of wanting us to do here, because we have a 1/2 and we have a 2. So we could work it out. So let's do that. So let's go to log base 2. So we're going to have log base 2 of 2 over log base 2 of 1/2. And then what it's going to have you do, because you can work this out using the fact that b to the y equals x and log base b of x equals y. So I'm going to come over here and let's see, log base 2 of 2 equals y. So I know 2 to the y equals my x. My bases are the same, so I know y equals 1. So the top of this is 1 over then I'm going to do the same thing to the bottom. So we have log base 2 of 1/2 equals y. So b to the y equals 1/2. So that 2 to the y equals, remember we get rid of that fraction by bringing the 2 up, and it makes the exponent negative. Bases are the same, so we know that y is equal to -1. And then 1 divided by -1 is -1. Okay, now we could have also taken this to like base 10, so we'd have just said log of 2 over log of 1/2. If we put that in our calculator, it would just tell us -1. All right, then vertical translations with product property. It says when graphing log functions in the form of y equals log base b of kx, we can show that the product property y equals log base b of k plus log base b of x is equivalent to a vertical translation of the parent function from a equals log base b of k. Then we have y is equal to a plus log base b of x. Let's explore this idea. So it says given g of x equals log base 2 of 4x, use the product property to show that this is a vertical translation of the function f of x equals log base 2 of x. Alright, so what it's saying here is because these two are being multiplied inside here, we know that we can separate them because when being multiplied, we can separate them by addition. So we're going to rewrite this as g of x is equal to log base 2 of 4 plus log base 2 of x. Now remember earlier said if you have a log base of a number, you should see can you simplify that. So I'm going to come over here and let's see if we have log base 2 of 4 is equal to y, then b to the y equals x. We can get like bases because 4 is the same as 2 squared. So we get 2 to the y equals 2 squared, and so we know that y is equal to 2. So that means that our function here, g of x equals log base 2 of 4 is equal to 2 plus log base 2 of x, which is the same thing as if we'd have written it as g of x equals log base 2 of x, and then we had a positive 2. So we can see there that that is a vertical translation of the original up 2. So now it says to graph both f of x and g of x on the grid at the right. Alright, so remember log base 2 of x is our f of x, which is the same thing as saying 2 to the y equals x. So when we go to build our table, we're going to pick some y values, and we're going to plug them in for the y and solve for x. So 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the first, and 2 squared. Remember, because it's a log, we have a vertical asymptote at x equals 0. All right. One and 4 is 2. And so we can see our graph right here. That's our parent function. Now for our new one, it's just our parent function up 2, so we're going to add 2 to the y values. So we still have our x's are the same, and our y's are going to go up 2. And my vertical asymptote doesn't get affected because it's an x value. So my vertical asymptote is the same. Now we're at 1/4, 0. 1/2, 1. 1, 2. 2, 3. And then 4, 4. And we can see here that it's the exact same graph, but everything's been moved up 2. Alright, it's a C says describe the change in the output values. Sorry. Describe the change in the output values over equal length input value intervals. So we know that as x increases by 1 unit, the y values shift up 2 units. I'm going to put vertically shift up 2 units. All right, and that is the end of lesson 12A.